Hello and welcome. So, we are at the last week of our course. In the previous 11 weeks, I have tried to give you a broad idea about matrix Lie groups and technicalities surrounding them, how you can realize them locally using Lie algebras, and how the Lie algebra corresponds to the ambient group by exponential map, the Lie bracket, which essentially defines a Lie algebra, and several examples. Now we are in the last week, so that's the end of this course. So in this last week, what I will do, I will give you a broad idea of how general Lie groups are defined and how Lie group and Lie algebra in general corresponds to each other. Only basic statements and ideas in the coming weeks. And I will also try to give you some applications of Lie groups in other areas of science. Now, what we will do before that, we have seen several examples, but with the most example that we have seen are general linear, special linear groups, and the compact orthogonal groups or compact unitary groups. Now, there are some other important examples of non-compact groups as well, and essentially the general linear, special linear, and these non-compact examples, they give you rough classification of all semi-simple or simple connected Lie groups, simple connected matrix Lie groups. So this is a deep result. We will not discuss this result, but if you know these broad families, these four families of general linear, special linear, and the two non-compact examples that I am going to discuss today and perhaps in the next class, that will essentially keeps all simple matrix groups up to Lie group isomorphism. Simple connected matrix groups up to Lie group isomorphisms. Okay, so these two examples that I am going to discuss are kind of important examples, and they are all, I mean, whatever matrix Lie group you consider, they in some way or the other they can be realized as subgroups of these four families, or essentially, see, if you take simple Lie group, these are the simple. These are all the simple matrix Lie groups. So if you take non-compact Lie groups up to certain equivalence or isomorphisms, they will be either of special linear, general linear, and one of these non-compact examples. And if you take compact Lie groups, matrix Lie groups, then you have already seen them. Okay, so this is pretty strong result, and this is a very deep result which follow from classification of complex semi-simple Lie algebras. Okay, however, this also is true over real numbers as well. Okay, so that's the intuitively or roughly what it gives you, but we will not go into full detail. We don't have time, but I do want to give you examples of these two non-compact simple Lie groups that I have mentioned once, but here we will see more detail about them, like connectivity, etc. So those will be the first two lectures, and these will be in kind of more detail than the other three lectures that will follow afterwards. So let's begin. Okay, so let's go through these non-compact examples. So to begin with, we equip Rn plus 1 with the non-degenerate symmetric bilinear form given by x comma y, where x is x naught, x1 xn, and y is y0 y1 yn. Then you define x comma y to be minus x0 y0 plus x1 y1 plus xn yn. Now note that this bilinear form is not positive definite, because if you take a vector v which is 1 comma 1 0 0 0, then the norm or the length of v with respect to bilinear form is 0. And in this Rn plus 1 equipped with this non-degenerate bilinear form, any vector can have norm positive, negative as well as 0. Now consider the set of all linear maps, invertible linear maps which preserve this bilinear form, and that we denote by On, 1. Okay, and it is called the Lorentzian orthogonal group. Now, sometimes when Rn plus 1 is equipped with this bilinear form, it is denoted by Rn, 1, and we will discuss a generalization of this thing. Now, any bilinear form on Rn plus 1 can be represented by a real symmetric matrix. So, you have any bilinear form B, and then if you choose a basis EI, E1 up to En, then B, EI, EJ, this matrix, so IJ, in this case it is n plus 1. Okay, so then B, EI, EJ, 1 less or equal to IJ less or equal to n plus 1. So this is the matrix for the bilinear form. Okay, but for that you need to fix a basis, and then you get a matrix for the bilinear form. So any bilinear form can be represented by a real symmetric matrix, because any symmetric bilinear form, any symmetric bilinear form can be represented by a real symmetric matrix. Thus, if B is a symmetric bilinear form, then you can write B x comma y as x transpose S y, where S is symmetric. Now note that this form, this Bxx, x transpose Sx, that is represented by a quadratic polynomial, and it is called a quadratic form. So corresponding to every symmetric bilinear form, you have a quadratic form, and corresponding to every quadratic form, you have a symmetric bilinear form, because you are over real numbers, so it is true. Now when this symmetric matrix S is invertible, B is non-degenerate. So non-degeneracy means if x non-zero, y non-zero, then bxy should be non-zero. Or in other words, if bxy equal to 0 for all y in Rn plus 1, then x is 0. Okay, so there is no vector that is orthogonal to every other vector. So this is not possible for a non-degenerate bilinear form. But in terms of the bilinear matrix, the matrix of the bilinear form, non-degeneracy means the symmetric matrix which represents the bilinear form is invertible. Now recall from linear algebra Sylvester's law of inertia, which tells that if you take any n by n matrix, symmetric matrix, then A is congruent to a diagonal matrix whose diagonal entries are 1 or minus 1 or 0. So that means you take any symmetric matrix A, then up to congruence, that means up to a multiplication by S, where S is the invertible linear map, S transpose will be this D. So there exists such S. That means you can always congruent or up to congruence, you can take all the symmetric matrices in this form D. Now when D is non-degenerate, it cannot have 0 as the eigenvalue. So in that case, any non-degenerate symmetric bilinear form is congruent to some diagonal matrix whose diagonal entries are 1 or -1, and we can club the 1 together, club the -1 together, and represent them as this block IP, Q, and we can denote it by dp, q. So it is essentially like, for example, 1 1 minus 1 1. This is one such example. Okay, so take any symmetric matrix up to congruence, they are of this form. So any non-degenerate symmetric bilinear form is congruent to one of these diagonal form. So they are all over real numbers. Okay, so if you consider them as your non-degenerate symmetric bilinear form or quadratic form, then up to congruence, they are given by this inner product, summation I equal to 1 to p minus xi yi plus summation I equal to p plus 1 to n plus 1 xi yi, where q is n plus 1 minus p. And such a bilinear form is called a symmetric bilinear form of signature p, q. Okay, or generalized inner product, but I would not call generalized, I will say call them as inner product of signature p, q. And it is represented by this diagonal matrix, which I denote by JPQ, which is the diagonal IP minus IQ. And any such bilinear form looks like you on Rn plus or Rp plus Q. Any such bilinear form looks like X transpose JPQY, where X is in R P plus Q, XY, both the vectors. Okay, so on Rp plus Q, on Rp plus Q. So this is the classification of symmetric bilinear forms, real numbers. So now you consider the matrices or the linear transformation. Okay, and yeah, P plus Q, and yeah, so one notation are, say, P plus Q equipped with JPQ is denoted by Rp, Q. Okay, so this is the notation. So now you consider all linear maps which preserve this bilinear form. They form a group, and that group is denoted by OP, Q. So this is a generalization of the group ON, 1 that we have started with here. Okay, so essentially this is the special case of OP, Q when P equal to 1 and Q equal to n. So we get a family of groups which preserves bilinear form, symmetric bilinear form over real numbers of different signatures. So these are nice groups. Okay. Now, as I told you, you take any symmetric bilinear form, you can represent them by matrix, and in this case the matrix is given by JP, Q. So all these linear maps which preserve this bilinear form, you can convert them into matrix notation, and in matrix notation OP, Q is the group of all n plus 1 by n plus 1 matrices which satisfy this identity. A transpose JPQA has to be equal to JPQ. That means A preserves the non-degenerate symmetric bilinear from JPQ. Now when P equal to 0 and Q equal to N, this is our usual Euclidean inner product. And observe that this identity becomes just A transpose A equal to identity, which we are very familiar with. And in that case, O0N is just O0N is just ON, which is compact. However, for P greater than equal to 1, Q greater than equal to 1, OPQ is not compact, we will see, but it's a small exercise that for P greater than equal to 1, Q greater than equal to 1, OPQ is a matrix Lie group. Now, how do you do that? What you want to show if something is a matrix Lie group, it is a closed subgroup of the general linear group. Now, to begin with, so this is a symmetric matrix. You can note that you multiply JPQ by any A, that also gives you a symmetric matrix. Now consider the set of all symmetric matrices over Rn plus 1. So then that's a Lie group, and this is isomorphic to Rn into n plus 1 by 2. Because if you take the symmetric matrices, what is the dimension? So you have this n plus 1 diagonal, they count for n plus 1 dimension, and then you have n plus 1 square minus n plus 1 by 2 real number. That's the degrees of freedom. So you take n plus 1 common, then it is n plus 1 minus 1. So n into n plus 1. So whatever, I mean, let's count the dimension of the symmetric matrices somewhere here. So take Rn. So then a symmetric matrix has n diagonal entries that count for n dimension, and then this part is same as that part. So you from n square minus n by 2. So this is n square plus n by 2, right? So n into n plus 1 by 2. So in our case, Rn plus 1, we have n plus 1, n plus 2 by 2. Got it? So I am just counting that kind of now how many variables you need to express the symmetric matrix. So for example, A, B, C, okay, D, and it is not D, this is B, E, F, and this is not F, this is C, F, H. So 1, 2, 3, 4, 5, 6. This portion is not needed. So 6, right? So this is 2 plus 1, right? So n equal to 2. So 2 plus 1, 2 plus 2 by 2, 6. So it's matching. So the dimension of all symmetric matrices of Rn plus 1 is n plus 1 into n plus 2 by 2, and you can identify them with this affine space. Now OPQ is disconnected and non-compact. So that's also another fact, but before that I tell you why it is closed. So you consider this map, A goes to A transpose JPQ A. Now this is contained in this is a map from GLN plus 1R to symmetric Rn plus 1. It's a continuous map, and OPQ is the inverse image of JPQ under this map. So it is closed. Okay, and why it is this? It is non-compact. So for proving non-compactness, you observe that SO 1, is contained in OPQ. Now you take any SO 1, then take a 2 by 2 matrix. Okay, and just compute what this identity A, B, C, D transpose A, B, C, D equal to 1, 0, 0 minus 1 give you. That will give you one embedded copy of SO1, 1 inside OPQ. If you do that, you will find that every element in SO1, 1 will be of this form: cosine hyperbolic t, sine hyperbolic t, sine hyperbolic t, cosine hyperbolic t. And it grows unboundedly as t goes to infinity. So OPQ cannot be bounded, so it is not compact. Now the final thing, it is disconnected. Now why it is disconnected? Okay, so note that the determinant of A, you take any A in OPQ, then this identity implies the determinant A can be plus minus 1. So the determinant map is continuous and it has two images, plus 1 and minus 1. So OPQ cannot be connected. So OPQ is disconnected. Now the question is, how many connected components OPQ has? Okay, so the claim is OPQ will have 4 connected components. So you take any OPQ, then it has 4 connected components for PQ greater than equal to 1. That's the claim. So we will discuss only the case when P equal to N and Q equal to 1, and the general proof will be similar. We will skip that. Okay, so let's discuss the P equal to 1, Q equal to N case. Now when P equal to 1, Q equal to N, what is the space? The space is Rn plus 1 J1, N. Now this is same as Rn, 1, okay, or R1, N, which are denoted by earlier. And the underlying bilinear form is xy equal to minus x1, y1, x2, y2, xn plus 1, yn plus 1. So here I have slightly changed the notation and I am taking x as y. I am counting these entries from 1 instead of 0 like I did a while ago. Okay, so now note that you can decompose Rn plus 1 into disjoint union of 3 subsets. V plus consists of vectors whose inner product is positive. V0 is the vectors whose inner product is 0, and V minus is the vectors whose inner product is negative. So this is the scenario. Now consider this conic, the set of all vectors in R1, N whose norm or whose norm x, x is minus 1. Okay, so this is a nice conic, and ON, 1 acts on HN tilde and it preserves it because ON, 1 preserves this inner product, so it preserves when it is minus 1, so it preserves this conic. Now note that x, x equal to minus 1. Now this implies x2 square plus xn plus 1 square plus 1 equal to x1 square. So this conic is given by all vectors x in Rn plus 1 that satisfy this identity. Okay, now the right hand side, you can take x1 to be negative as well as you can take x1 to be positive. So the picture in dimension 2 is following. So in dimension 2, what happened? You have 3 dimensions, then this is the conic for which x1 is, so this is x1, okay, this is x1, x2, x3. So this conic, this is x1 greater than 0, and you have a copy of this hyperboloid for which x1 less than 0. This is r2 comma 1 and h2 tilde. Okay, and these are all vectors xx equal to minus 1. So you see there are two components of hn tilde. One corresponds to when x1 is positive and the other corresponds to when x1 is negative. Okay, so hn tilde has two components, and on comma 1 preserves hn tilde. Now you have one disconnected set, two components, and on comma 1 preserves the hn tilde. What does it mean? That means either it preserves each of these components or it swipes them, right? So clearly on comma 1 has two connected components. One preserves them and one swipes them, and depending on determinant 1 or minus 1, for each of these components there are two more components, making it total 4. Now I explain it in a slightly more elaborate way. So instead of swiping the components, suppose you consider SON comma 1. So ON comma 1 has already two components. One corresponds to determinant 1 and the other corresponds to determinant minus 1. Now collect SON comma 1, the determinant 1 matrices, the subgroup of ON comma 1 consisting of determinant 1 matrices. Now the component of SO1 comma 1 that preserves HN tilde preserves HN. So the component that x1 greater than 0, call it HN, and the other component you call it HN minus. Okay. So the component that preserves HN is the one containing identity, because if x1 greater than 0, it's easy to see, right, that how you sort of get a basis for this. You choose the canonical basis E1 up to En plus 1, and further you can choose the basis in a way such that E1 equal to minus E1 and EJ equal to 0, not 0, 1, J equal to 2 to N plus 1, and EJ equal to 0 for all I not equal to Z. So this is the same Gram-schemed orthonormalization process that gives you, but here you can choose the basis such that E1, the one representing x1, is orthonormal and of norm minus 1, right? So E1 belongs to HN tilde, and E1 you can take to be the standard basis 1 0 0 0. So it belongs here. So SON comma 1, the one that maps 1 0 0 0 to this component, okay, right? So that must be the identity component, because the identity map fixes C1. So it must preserve this component. So the component that preserves HN must contain the identity. So SO naught N comma 1, the component of so SO naught SO N comma 1 that preserves HN is the one containing identity, and the one that does not contain identity. So the other, so SON comma 1 has matrices that preserves this upper half hyperboloid or HN, and it has also matrices which swipes them. So SON comma 1 has two components, one containing the identity and another swipes HN and HN minus. So SON comma 1 has two components. Similarly, SO minus n comma 1 also has two components. So ON comma 1 has a total of 4 connected components. So this proves this result. Now note that the positive hyperboloid, the upper half hyperboloid, or Hn, which consists of all vectors of norm minus 1 and x1 greater than 0. This is the hyperboloid model of the hyperbolic space, the so-called hyperbolic space, and it is a prime example of a non-Euclidean space. One can show that it is diffeomorphic to the unit ball Dn in Rn, and it's very interesting space. I mean, it has lots of nice geometric properties, and it's a very important space in mathematics. But this example demonstrates that ON comma 1 has a 4 connected component. Similarly, one can show that OP comma Q also has 4 connected components, and it is non-compact for P, Q greater than or equal to 1. Now, other than this, there are other non-compact groups one can construct similarly, and these are these families: SOPQ, SUP comma Q, SPP comma Q, and the construction is just similar. SOP comma Q means you take all elements from special linear group that satisfy this identity, A transpose JPQA equal to JP comma Q. Now there is a Sylvester's law of inertia for complex Hermitian form as well. You take any Hermitian form up to congruence, you can express it as JP comma Q and consider all matrices which preserve this Hermitian form. That means they satisfy this identity, A bar transpose JPQA equal to JP comma Q. Okay, it is not necessary for you to take A to be from special linear group. You can drop a special linear group and you can define it as UPQ also, but we just take determinant 1 here to make it as per the quaternionic case, where SPPQ means they will always have determinant 1, okay, and A bar transpose JPQA is JPQ. Now here SLH means quaternionic determinant 1, which you know already, right? So you embed a quaternionic matrix into complex matrices and then take the determinant of the complex matrix. So these are the 3 families which are examples of simple non-compact groups. Okay. Now among them, SOP comma Q is non-compact and it is disconnected. It has 2 connected components. But the other 2 are non-compact and connected. Now why they are connected? You think about it. Okay. You can prove it using the kind of ideas we have already seen, and their non-compactness follows similarly as in the SOP comma Q case. Okay, so these are groups which are of geometric interest, and you are now familiar with these groups to some extent, and just keep it in mind that these groups are there and they play a big role in geometry. If you want to see more details about them, you look at these books by on what is called as symmetric spaces. Okay, but for me, I think I wanted to give you examples of more non-compact groups, and this is the first set of examples that I have given. In the next class, I will give you another set of examples, and we will discuss some basic properties of that example as well. But as of now, for today, that's it. So thank you very much. See you in the next class.